So we have one final talk for today in this session, and the speaker is Faria Sana. And Faria is a graduate student in my lab. She's actually the first member of my lab, and she's been dropping me subtle hints of how light Steve's Mac Air computer is, and it shows how heavy her 4-year-old computer is. And I really need to credit Faria with bringing a whole new area of expertise to the lab. Faria has done an amazing job, largely independently, I would say, bringing in this area of expertise on interleaving into the lab. So please join me in welcoming Faria Sana.
Thank you. So if you were here in the morning, one of Catherine's slides discussed a study in which they calculated the utility of several learning designs. Interleaving was only scored as being moderate. And in Carl's talk, we noticed that statistics is quite boring. So maybe I should go home. Or hopefully by the end of the talk, we can increase some interest in statistical learning and maybe some utility in interleaving in the context of statistics. So the standard format in all schools is to organize course material into modular lesson plans. This means that the instructors focus on one particular topic for a few days, and then they move on to the next topic, and so on and so forth, until they've taught all the components of the course in discrete blocks. So this is consistent with the way that textbooks are set up as well, where each chapter is dedicated to a single topic with end-of-chapter practice problems that students can practice and master. So for instance, the typical classroom procedure in an undergraduate statistics course is to introduce students to a new topic, so say they're going to learn about t-tests, and give them many example problems on the procedure to make sure that they know it. With this type of learning, students feel more confident in their ability to solve t-test problems and think that they know the concept really, really well. And so it makes sense, it makes intuitive sense to sort of focus on one topic, master it, and then move on to the next one. However, research indicates otherwise. So what's wrong with that? So once students have finished studying, say, the basic procedures of a t-test, they'll have to use those procedures in many different contexts. And so it's important to know how to solve a t-test, but it's just as important to know when to solve it. And so practicing one topic at a time can boost your confidence, but you'd still struggle to remember which concept applies to which problem, and that's exactly what you need to do on a final test. And this is likely because students perhaps don't get enough mixed practice, which promotes how one concept differs from another and what the different features are that make up a concept. And so ideally typically when students learn a new topic, they review the basics, they practice several problems, they reach an acceptable level of proficiency, and then they move on to the next topic and they do the same thing again. This is called blocked practice. And interleaved practice, on the other hand, is really working with multiple topics in parallel or at the same time. And so the seductive, fluent nature of blocked practice is very hard to resist. I mean, the learning curves seem fast, it seems like an intuitive way to study, which is why blocked learning is so dominant in educational contexts. But research has shown that memory in the long term is actually better for topics that are interleaved rather than blocked. So, and this is what we call the interleaved effect, the benefit of interleaved practice on long-term retention. So when students are learning statistics, they're at least at an undergraduate level, they are most concerned with the mechanics, so plugging numbers into formula and working around trying to figure out how to work on SPSS, and that's all that they focus on. Whereas the real skill is actually the conceptual skills that you need to be able to understand when a problem is an independent t-test and when a problem is a dependent t-test. And so I'm interested in whether we can apply the interleaving effect to promote this kind of conceptual statistics learning. And so if students are introduced to several concepts and given practice problems, would interleaving allow them to better categorize the problems based on specific features? The key insight for these problems, I won't leave you in suspense, is that one of them is an ANOVA, whereas the other one is a paired t-test. So in today's talk, I'll share some data with you to demonstrate that interleaving practice can be implemented to learning statistical concepts. The results also offer some insight as to why interleaving is beneficial, whether it's always beneficial, and I think most important, whether it equally benefits all students in a classroom or not. So the typical experiment that tests interleaving has a study phase and a test phase. In the study phase, you manipulate the presentation schedule of different concepts. So say you want to learn concepts A, B, and C. You using several practice problems. A blocked session looks something like this, where you practice all the examples of concept A and then you move on to B and then C. An interleaved practice session would look like this, where you mix all the problems of all concepts and practice them together. In the test phase, you're tested on how well you know these concepts. And the finding again is that interleaving practice leads to better concept learning than blocking practice. Interleaving effect is a very general phenomenon. What I mean by that is interleaved schedules can promote multiple forms of learning, so motor movements, basic memory of words, and it even extends to generalization and application of learned information. Now, researchers are trying to see if they can apply this effect to educationally relevant materials and contexts. So this brings me to my first research question of whether the benefit of interleaving can generalize to learning of statistical concepts. The general method that I use in all my experiments that I'll report today is identical. There's a study phase, there's a test phase. In the study phase, participants study exemplars of 3 non-parametric statistics concepts. So chi-squared, Wilcoxon sign, and Kruskal-Wallis. So participants learn these 3 concepts. Each of the concepts is illustrated by 3 simple examples. And their task is to study the examples and recognize the important features of a concept. They're told that they'll be tested on their knowledge about these concepts. Then, following the study phase, participants do a 5-minute distractor task, and then they write a test. So this transfer test consists of 18 new word problems, and they look something like this. And so basically, they're asked to read each problem carefully and select the most appropriate statistics test that you would use to solve the problem. And so all my study and test materials are modified from an undergraduate statistics textbook. They're modified because each concept is defined by 4 important features which form the basis of all these problems. So to examine if interleaving can generalize statistics concepts, the presentation schedule was manipulated so that all examples of a concept were together, or each concept example was mixed with examples from other concepts. And then at the end, everybody wrote the same transfer test. So here we see on the y-axis proportion correct on the transfer test as a function of whether they were in the blocked or interleaved condition. And we do see that we've replicated the interleaving effect using statistics materials to show that practicing problems of different concepts together results in better classification of those concepts than when practicing problems one concept at a time. And to put this in an educational context, this is actually a huge difference from a C to an A minus. And so to answer our first question of whether interleaving can generalize to stats, well, it seems like it does. So why is that? Why is it that we see this benefit of interleaving? What is so special about it? So when examples of multiple concepts are interleaved, the examples of any one of those concepts is also spaced apart in time. And this is for all concepts. So the interleaving effect, is it simply due to the temporal spacing, or is there another mechanism that's driving this interleaving benefit? One theory is that interleaving promotes discriminative contrast. When learning to distinguish between 2 very similar concepts, it's very difficult to identify the subtle differences between them. And so interleaving enhances this discrimination contrast between concepts, and it helps hard when you're practicing in a blocked manner, because when you're practicing a concept over and over again, not only do you know what's coming up next and you don't try as hard, but it makes it also very difficult to notice the subtle differences. So to test whether interleaving is simply a magnified spacing effect or if it promotes generalization or discrimination learning, we had two conditions in which all examples were interleaved with different concepts. One was sequential, so that means it was presented one after another. And in the other condition, we inserted temporal spacing between successive example presentations. The temporal spacing was filled with a 25-second cartoon filler, with different cartoon fillers presented each time. So again, we had two conditions, both interleaved, one with temporal spacing and one without. So, and then finally, they all wrote the transfer test at the end. So discrimination is what enhances learning rather than temporal spacing. We should see greater performance on the final test when concepts are interleaved without temporal spacing than when concepts are interleaved with temporal spacing. And this is because temporal spacing should disrupt the processes that are essential for noticing differences. And so here again we see performance on the transfer test as a function of condition, and we see that adding temporal spacing did not enhance learning for interleaved concepts. In fact, adding temporal spacing decreased performance from 81% to 69%, consistent with the hypothesis that perhaps adding this temporal spacing may have disrupted discriminative contrast processing from occurring. And so it seems like the reason why interleaving is beneficial is because juxtaposing different concepts next to each other highlights the differences between them. So far we've established that interleaving practice is better than blocking practice, and the reason why is because it promotes discrimination learning. So is interleaving always better than blocking, or can blocking be as effective or even more effective than interleaving depending on several factors? So if the ultimate goal is to learn of concept learning is to be able to classify new examples into appropriate concepts, then sure, interleaving allows you to distinguish between the concepts. Or perhaps blocking can allow you to extract the common features that define a given concept. And so in most studies, the examples are presented sequentially, so they're presented one at a time. But perhaps there's reason to believe that benefits of blocking are enhanced under conditions in which participants are allowed to see the examples simultaneously. Now, there are a few reasons why we think simultaneous presentations might be better than sequential presentations. For one, it can reduce memory constraints and noise related to an imperfect retrieval, and that might allow learners to make better comparisons, more effective comparisons, and extract the relevant features. Second, spontaneous comparison has also shown to, or simultaneous presentations have also shown to foster spontaneous comparisons, especially for individuals in the blocked condition, as they might allocate initial attention to features differently depending on whether they're presented with multiple or just a single example. And so, can simultaneous presentations then draw attention to commonalities within a concept? To test this, we had two sequential presentations, blocked and interleaved, and a third condition in which examples of a concept were presented simultaneously. Time on task was obviously controlled for, and we expected that the blocked simultaneous condition would do just as well or better than the interleaved condition. And all participants then wrote a final test, transfer test. Here we see, again, performance on the y-axis, performance on the transfer test as a function of condition. So we here replicate the interleaving effect, the interleaving benefit, showing that interleaved practice is better than blocked practice. Now, for the blocked simultaneous condition, we do see that simultaneous presentation enhances learning as much as interleaving does. And perhaps we speculate that it might be because when blocked practice is sequential, memory of features that define a concept are not very old, creating fluency in learning, and that can diminish attention across several exemplar presentations. Now, this attention deployment is still probably still occurring when examples are presented simultaneously, but perhaps the initial presentation with the 3 examples enhances the quality and perhaps quantity of the concept schema that's created because it's facilitating the abstraction of these common features. And so it actually, if you look at it from an educational perspective, puts the participants' performance in the blocked simultaneous condition and the interleave sequential on equal footing, which is a huge deal, again, going from a C+ to an A-. And so, is interleaving always better than blocking? No. Blocking might be as effective as interleaving, as each can foster different types of comparisons that are both important for concept learning. So the question now is not simply whether interleaving promotes learning of statistics concepts, but also why it's best, when it's best, and for whom is it best. So interleaving, is it a one-size-fits-all technique, or is the magnitude of interleaving larger for one group over another? So there are a lot of individual differences that students bring in with them into classrooms, and many of these differences can perhaps affect the benefits of interleaved practice, such that perhaps interleaving might be better for one student, but not for the other. One well-studied and important individual difference is students' working memory capacity. Working memory is an attentional mechanism that is used to maintain current task goals, process incoming information, retrieve information from long-term memory for integration, and all in the face of some sort of interference or distraction. Working memory is where learning actually takes place. Even when you're trying to comprehend what I'm saying, is your working memory in action. And so students with higher scores on working memory are better able to, or are better at coordinating their attention to relevant features of a problem and are less likely to be distracted. Effective functioning of working memory then influences the extent of learning that occurs. So not surprisingly, working memory capacity is related to a host of academic skills. Even simple math problems require storage, retrieval of facts from long-term memory, and processing. And so, in fact, individual differences in working memory capacity measured a year before predicts attainment measures in reading and math, suggesting that perhaps working memory drives academic development. And impairment in working memory actually might result in poor academic achievement. So how is performance on working memory related to the interleaving effect? So one line of research speculates that the advantages of interleaved practice may depend on working memory-dependent processes. The assumption is that examples of several concepts during interleaved practice must be actively maintained in working memory to allow for efficient comparisons between them. So based on this account, interleaved practice is quite dependent on working memory because it requires learners to maintain attention to the task goals for comparison, allocate attention to relevant features, not be distracted from irrelevant features, and successfully integrate information with knowledge in long-term memory. And so, interleaving might impair learning for learners with lower working memory capacity because all these demands are taxing. Or perhaps the juxtaposition of different concepts, although desirably difficult, can actually enhance the salient differences between the concepts. And so, perhaps compared to blocking, interleaving might actually foster more elaborative and meaningful comparisons for learners with lower working memory. So to test these two hypotheses, participants practiced statistics concepts either blocked or interleaved. And then they wrote a final transfer test, which has been the same across all studies that I've reported. And then they also finished a working memory test. This is a 20-minute working memory task, and essentially what we do is you get a score after you finish it, and the top 25% and the bottom 25% of the scores are used to categorize participants as having high or low working memory, respectively. And so here again is performance on the transfer test. So this is, the two bars are performance for individuals categorized in the higher working memory group. We see that these individuals don't really benefit much from interleaving, but this isn't too surprising because research does suggest that this group uses more efficient strategies to abstract critical information and probably are better at retrieving and integrating existing concept examples from long-term memory to make the comparison. But participants with lower working memory perhaps need immediate juxtaposition to make the differences more salient. It seems actually like the interleaving benefit observed here is really driven by participants with lower working memory. And so, is interleaving a one-size-fits-all technique? Doesn't look like it, but the good news is that interleaving mediates differences in cognitive ability such that it acts as a tool to improve learning among learners with lower working memory without compromising learning for learners with higher working memory. And so interleaving practice has recently become the sexy teaching and learning thing within the context of education. And so although it's one of the promising principles and has real potential to promote learning, it still needs more refinement with applied studies in the classroom to yield more definitive strategies for educators and instructors. And so it seems like the benefit of interleaving complex conceptual knowledge seems to have boundaries that need to be further examined. So interleaving seems to only be beneficial if topics or concepts being interleaved are very similar or related. Some data from our lab suggests that interleaving can actually impair learning if concepts being learned are too dissimilar or too difficult. So perhaps here, you might start looking into hybrid schedules where you do a little bit of blocking initially to sort of better understand the concept, and then you start to interleave. And we're still not sure if interleaving entirely different topics does anything to learning. And so there's a lot of work that still needs to be done. Instructors, however, based on what we do know, can incorporate interleave practice into students' learning by reviewing topics covered in previous lectures at the beginning of each class, having cumulative tests, that's always good, and give homework assignments that include items from previous chapters. So even if the book covers one topic and then gives blocked practice on that topic, homework assignments or in-class exercises can mix up these types of problems. So, and for students, interleaved practice can be accomplished by mixing up topics within a particular domain during periods of study. So for instance, student can mix topics, mix concepts together from different chapters covered in a statistics course to study for an upcoming exam. So to conclude, we do have a few groups of cognitive scientists exploring research questions like these to sort of determine the boundaries of the interleaving effect within the context of education. And it's really encouraging to now see initiatives like this that specifically aim to sort of bridge the gap between the two. And I'm honestly really glad to be a part of it. Thank you.
We have time for a couple of questions from the audience.
Thanks for a really interesting talk. I had a question. I thought it was really interesting what you found with low versus high working memory. And of course, because I've worked with kids so long, I'm wondering what implications this has, because children generally have a smaller working memory than older adults and older children. And then I was just also wondering, tied in with that, how much learning children do at the moment that is naturally interleaved versus blocked. Because I know that for certain children, I think they learn generalization first. So they'll look at a feather falling down from the ground and they'll be like, bubble, you know, and then it's only later that they learn discrimination. So I just thought I'd throw that out there as just an amusing topic.
I'm not too familiar with the developmental literature, but I do know that a group of UCLA students or researchers have looked at the effects of spacing and interleaving, so inductive learning, in kids or in toddlers, I believe, and they did still see benefits of spacing and benefits of interleaving. So, and I'm not exactly sure how working memory can play a role in this, but it seems like some of the literature suggests that individuals, younger adults with lower working memory, are akin to perhaps older adults and normal functioning working memory. And so perhaps we might also see that interleaving specifically benefits them, but to be honest, I'm not too sure. And I think that there haven't really been that many studies looking at the mediating effect of interleaving in different populations. But I mean, that's a very valid question and should be examined. Thanks.
Thanks, I really enjoyed the talk, especially if you're giving me some ammunition when the students complain, so skipping around their stats textbooks. But I was wondering, the interleaving seems really well suited to understand which of the statistics tests they should be using. But did you get any evidence that interleaving could improve the depth of understanding any one of those topics?
So I think that the literature on interleaving has really focused on words or motor movements, and I think that they're starting to look, now we have evidence to suggest that interleaving math problems is really good because it helps you understand when to solve what procedure. In terms of depth of knowledge, I don't think that we've done very much with that, and which is sort of why I suggested that, there's so much evidence for interleaving, but in terms of educational context, there's very little to use as prescriptions. I don't know, but I'm speculating that when you're really trying to deeply learn a concept, and if the task is for you to discriminate one concept from another, interleaving can help you develop a better conceptual schema of all the features that make a concept, and why that concept would be different from other concepts. And so that would tap into the depth of learning, the depth of conceptual learning, if that makes sense.
Thank you, Faria. That brings us to the conclusion for our presentations. I want to thank all of our speakers from both sessions today for some really wonderful things to think about. Just a couple of announcements. If you are here, or if you are attending the workshops tomorrow, they'll start at 9 a.m. sharp, and they'll take place in room 1009, just down the hallway over there. If you are interested in taking a tour of the live lab, please meet at the reception desk at the entrance where you got your name tag. And if you're planning ahead, we actually have a date set for EdCog 2015, August 12th to 14th, featuring Sylvain Marino, who casually agreed to give a talk this morning at the poster talk. Lastly, if Michelle and Irina, could you please stand up for a second? These are the two women that actually make this happen. David Shore and I are listed as the co-organizers, but all we do is think of things to do. And wouldn't it be great if we did this? And then Michelle and Irina actually make all these things happen. So please join me in thanking Michelle and Irina. And with that, thank you, and hope to see you next year. And for those who are coming to workshops, we'll see you tomorrow morning. Thank you.